So what exactly is electromagnetic radiation? Well, it's a wave of energy. So let's say we have this electromagnetic radiation propagating through space. What is it made out of? Well, it's made out of two key components. First, it has an electric field component, where here we have a weak electric field, here it gets stronger, here the electric field is really strong, then it gets weak again, then weaker, then it starts pointing in the other direction, because we know these electric fields are vectors. Then it points in the other direction and it's stronger, then it's really strong pointing in the other direction, and etc. Then we have this oscillating wave-like pattern. So again, that's one component, and we know if we had a charge, if we had some kind of charged particle and threw it in this electric field, it'd feel a force, because that's what charged particles do when they enter electric fields. So that's what electric fields are. So that's one component of this electromagnetic radiation, but it has another component. It also has a magnetic field component, where again, if here we had a strong electric field, then here we would have a strong magnetic field. Here we had a weak electric field, so we would have a weak magnetic field. But these electric field and magnetic fields will always be 90 degrees. They'll always be perpendicular from one another. And then they're related. So if this guy's strong here, then this magnetic field here will be strong, and etc. So that's one way to thought. So that's what electromagnetic radiation is. It's made out of these two components, and they actually propagate each other forward. It's this electric field here that reacts with this magnetic field, and they propagate each other forward. So that's one way to think of electromagnetic radiation, as this wave, as this oscillating wave of these oscillating fields. But there's another way. You can also think of it in terms of particles. So really, you can also think of it in terms of these photons. So these photons, these particles, make up the electromagnetic radiation. It's these photons, it's these particles that make the waves. And if that's a little confusing, that's normal. Everyone this is not intuitive, but you can think of it in two ways, either in the form of those waves, those oscillating waves, or you can think of it in terms of these particles, these photons. And it's these photons that make up the electromagnetic radiation, the waves. And these photons have energy. They're packets of energy. These photons have a certain amount of energy depending on the frequency of the electromagnetic radiation. So what do I mean by that? Well, again, now let's focus on the wave, and let's just focus on the electric field vectors, just so it looks a little more clean. So one really important formula to be aware of whenever it comes to electromagnetic radiation and all waves in general is this. The velocity of the wave equals the wavelength of the wave multiplied by the frequency of the wave. So something important to realize is all types of electromagnetic radiation, they'll always have a velocity of 3 times 10 to the 8 meters per second, which is really fast. This is a huge velocity. In fact, this is the speed of light. This is the speed of light because light is a type of electromagnetic radiation. So all types of electromagnetic radiation have a velocity of 3 times 10 to the 8 meters per second. And in fact, this can change if this wave enters into a new medium. This can change, but generally speaking, the velocity is constant at this 3 times 10 to the 8 meters per second. So what is the wavelength? Well, we know what wavelength is. It's the distance between these two peaks. It's once we've had one full cycle and we've repeated to the original cycle. So that's what a wavelength is, and again, it's a unit of length, maybe meters or nanometers, etc. But what about frequency? What is frequency? Well, a frequency is how many times something happens per second. So in this context, the frequency is if we were standing right here, let's say we were standing right here, and we were counting as this wave traveled with this velocity, as it traveled. In 1 second, how many wavelengths crossed through this location in 1 second? So I know that's a little abstract, so let's do an example. Let's say we have this electromagnetic radiation and it's moving with this velocity. And let's say it happens to have a wavelength of, let's say, 2 meters. Then if we were to stand right here, and if we were to count in 1 second, how many of these wavelengths pass through this region in 1 second? That value is our frequency. And again, that might seem complex, but it's a simple calculation. We know the velocity is 3 times 10 to the 8 meters per second. We know the wavelength is 2 meters. Now, with some simple algebra, we can solve the frequency, and we would get a frequency of 1.5 times 10 to the 8 hertz. So that means that's our frequency. So that means in 1 second, if we were to stand right here in 1 second, 1.5 times 10 to the 8 wavelengths cross through this region in 1 second. And that's what a frequency is. So again, so let's do, and it's something important to realize is this wavelength and this frequency, they're intimately related. But let's do an example. So let's say we have two types of electromagnetic radiation. Let's say we have an X-ray, which is one type of electromagnetic radiation, and let's say we have a microwave, which is another type. So we know because there are types of electromagnetic radiation, they'll always have a velocity of 3 times 10 to the 8 meters per second. So they both have the same velocity. But let's say this X-ray has this wavelength, while this microwave has a longer wavelength. Well, we see the way this math works. The velocity is constant. So if velocity is constant, we know if we increase wavelength, the frequency must decrease. It must decrease for this value to still equal velocity. That's just simply how the math works. So we see as the wavelength increases, the frequency must decrease. So this guy's frequency must have decreased. So this guy must have a smaller frequency. So again, and that's just the way that the math works. So that's something you should be pretty familiar with. But again, these are intimately related. And when talking about, when trying to categorize or characterize this X-ray, we can describe it in terms of its wavelength, or we could describe it in terms of its frequency. They essentially tell us the same thing. If we know the wavelength of this X-ray, we know its frequency. Because again, if we know the wavelength, we just plug it in. We know the velocity, so we can determine its frequency. So if we know the wavelength of this wave, we know its frequency. And if we know the frequency of this wave, we know its wavelength, just simply using this equation. And again, so what determines why is this called an X-ray and why is this called a microwave? Well, there are different categories, there's a spectrum, different types of electromagnetic radiation, and it's the wavelength that determines what kind of electromagnetic radiation you are. So if you have your wavelength is in a certain category, it's an X-ray. However, if we have another type of electromagnetic radiation with a different kind of wavelength, a different length in its wavelength, then it'll be a different then this would be a microwave. So what exactly do I mean? Well, here's the spectrum. So again, you can either focus on the frequency or you can focus on the wavelength. But let's say we have this electromagnetic radiation traveling through space, and let's say it happens to have a wavelength of, let's just say, 100 micrometers. Well, if we have an electromagnetic radiation with a wavelength of 100 micrometers, then it's a microwave. And again, let's do another example. Let's say we have a different electromagnetic radiation. Let's say this electromagnetic radiation happens to have maybe a frequency of 10 to the 19 hertz. Well, again, we see based on the spectrum, if we have a frequency of 10 to the 19 hertz, then that's an X-ray. So again, you can either focus on the frequency or the wavelength. It really doesn't matter, but for this video, let's just focus on the frequencies. If you know the frequency of the electromagnetic radiation, you know what kind of electromagnetic radiation it is. And there are these types. There's radio waves, which is a type of electromagnetic radiation. There are microwaves, which is another type. There are infrared waves. There's visible light. There's visible light that we're familiar with. There's red light and orange light and purple light. There's ultraviolet radiation. That's another type. There are X-rays and there are gamma rays. But what determines if it's a gamma ray or versus a microwave? Well, it's its frequency. If it has a certain frequency, it's a gamma ray. If it has another frequency, it's a radio wave, and etc. So if you know the frequency of the electromagnetic radiation, you know what kind of wave what type it is. And again, if it's smaller than 10 to the 11 hertz, then that will all be in the radio wave category. If it's larger than 10 to the 20 hertz, that'll all be in the gamma ray category. And the way I like to personally remember this is I like to remember colors in the middle. Then I remember violet is here. Then I remember ultraviolet, then X-rays and gamma rays. But look, U, V, X, Y, the alphabet. So that's personally how I remember this order. And I remember this order because in a day, how many minutes do you listen to a radio? Well, when you drive to work, maybe you listen to a radio 30 minutes. How many minutes do you use a microwave? Well, when you cook your food a couple times a day, maybe 5 minutes. And infrared, well, I know when you use a clicker for the remote control that uses infrared, so maybe you use that for maybe just 30 seconds. But so that's how I like to remember. We use, in our daily lives, we use radio waves a lot, we use microwaves a little less, then we use infrared less. So maybe that's not as helpful, but this is, that's pretty cool. So in something else is, again, if we know the frequency of the wave, we know what kind of type of wave it is. But the higher the frequency, the more energy there are in the photons that make up that electromagnetic radiation. So what do I mean? So let's say we have two types of electromagnetic radiation. Let's say we have a gamma ray, which we know has a very high frequency. And let's say we have a radio wave, which we know has a very low frequency. Well, we know the higher the frequency of the light, the more energy there are in the photons that make up that light. So we see this gamma ray has a much higher frequency. So therefore, if it has a higher frequency, that means the photons that make up this gamma ray have more energy. Because again, we know we can also think of these waves in terms of their photons. So again, this gamma ray has a very high frequency. So therefore, the energy in these gamma rays, the photons have a lot of energy. They're high energy. However, this radio wave has a very low frequency. So therefore, the lower the frequency, the lower the energy there are per photon in the photons that make up the electromagnetic radiation. And it's important to realize these are very general numbers. It's really, if you're curious, there's an exact spectrum with the exact numbers that determine whether it's a radio wave versus microwave. But these are just very general ideas just to give you a ballpark figure of what kind of hertz is an X-ray and what kind of hertz is a microwave and etc. But again, we know the higher the frequency of the electromagnetic radiation, the more energy there are per photons, per individual photon. So let's do an example. And again, so how exactly do we determine? Let's say we have this electromagnetic radiation, and let's say it happens to have a wavelength of 200 nanometers. What type of electromagnetic radiation this is? Well, again, if it has a wavelength of 200 nanometers, we see that would fall under this range. So this must be a microwave. It falls in this general range, so this must be a microwave. And again, we know if we know the wavelength and we know its velocity, we can determine its frequency. We know if we know its velocity and its wavelength, we can determine its frequency. So this guy has a frequency of 1.5 times 10 to the 15, which again, we see based on that where that would fall. And actually, this is a nanometer. So sorry, this was 200 nanometers. So it's a 200 nanometer wavelength. So therefore, if it has 200 nanometer wavelength, it's ultraviolet. So this is an ultraviolet type of wave. And then again, we found its frequency, which would fall in this general category. So sorry, so this was 200 nanometers. So again, the point is, if you know the wavelength, you know what type of electromagnetic radiation it is. Or if you know the frequency, you know what type of electromagnetic radiation it is. So you can either focus on the wavelength or the frequency. But we already explained how if you know the frequency, we said the higher the frequency, the more energy there are per photon. So in fact, we can use this formula. The energy per photon of an electromagnetic radiation equals this Planck's constant, which is just a constant. It's just a constant that you can just find in any old textbook, multiplied by the frequency. But essentially what this formula tells you is if we have this electromagnetic radiation, all you need to know is the frequency. As long as you know the frequency, you can plug it into this formula and you can determine how much energy there is per photon. So we have this electromagnetic radiation, we know the wavelength, so we know what type of electromagnetic radiation it is, and we know the frequency, and now that we know the frequency of this electromagnetic radiation, we could just plug it into this formula, multiplied by this Planck's constant, that would give us the energy, and that would spit out an energy of 1 times 10 to the negative 19 joules. So that's how much energy there is per photon, because we know this wave is made out of photons, so each photon has this much energy. And again, we also know velocity equals frequency times wavelength. So if we divide both sides by wavelength, we essentially get this formula. So we know frequency equals velocity divided by wavelength. So again, we know this equals frequency. And so therefore we know we could really plug this in for the frequency. So if we plugged in, because again, this equals frequency. So therefore we could plug this in. And if we were to plug this in, we'd essentially get this formula. So this is another type of formula, another form of this formula. So what this formula tells us is if you have an electromagnetic radiation wave, and if you know the velocity, and you know the wavelength of that wave, you plug it into this formula, you multiply by Planck's constant, that'll give you how much energy there is per photon. So we know each photon of this wave has 1 times 10 to the negative 19 joules. So again, the key point when characterizing an electromagnetic radiation wave, you can either focus on the wavelength or the frequency. It doesn't really matter which one you focus on, but for example, if you know the wavelength of this electromagnetic radiation, you just see where it falls in the spectrum. And you see, based on where it falls in the spectrum, you can determine what type of electromagnetic radiation this is. So we can tell this must be an ultraviolet form of electromagnetic radiation.